All right, so let's actually start using these vectors. I really enjoy these problems. Okay, so a Boeing 737 aircraft maintains a constant airspeed of 600 miles per hour, and it's headed due south. But as it's flying, this jet stream is acting on it. And that jet stream is 60 miles per hour, and it has this direction. And we talked about this so long ago. That's bearing 30 degrees east of north. So if you need a refresher on bearing, you want to check out the triangle trigonometry videos from our first week. It goes into bearing then. So if you think about, if I've traveled so much to the East Coast because that's where I'm from, when I go to the East Coast, the plane ride is about like 5.5 hours. And when I come from the East Coast and I come back to the West Coast, it's like an hour shorter. So it's because those winds are acting on the plane when I'm heading towards the East Coast. So what we're going to be asked to do in this problem is we're going to want to actually find the actual speed of this aircraft, because that wind is acting on it. So it's not necessarily going 600 miles per hour, and it's affecting how its direction. So that's going to be our goal, is we're going to figure out the actual speed and the actual direction, because then the aircraft can fix it so then it actually heads to where it needs to head. So again, good old diagrams are our best friend. So with bearing, this is north, south, west, east. Okay, well, I have this aircraft. I'm going to go ahead and give myself red. It's headed due south. We know it's 600 miles per hour. So that is your magnitude. We also could figure out our direction because it's headed due south. So that would be 270 degrees. You can use degrees or radians. I will say, since we're given degrees there, we're going to use degrees. Now, this jet stream is acting on it, and it's 60 miles per hour with a direction of 30 degrees east of north. So again, if you need a refresher, you're going to check out that video. So we have, let me not use purple, east of north. So it's heading this way, and it's only 60 degrees. Now remember, with bearing, your direction is always attached to the north or south line. So just seeing that diagram, I hope it's starting to make sense that this thing is being pulled this way, right? My aircraft is being pulled this way since this jet stream is heading this way. So what we're going to do is we're going to actually find the resultant vector, which is we're going to add these two vectors together to see how this jet stream is affecting this aircraft. And this is how it would be set up when I ask you on your final. I'll set it up like A, B, and C, so it walks you through. The first thing I need to do is I need to express the velocity. We're going to name it V sub A. That V sub A is just for aircraft. And then the V sub W is for the jet stream, so like wind. And we're going to put them in terms of I and J. And what's going to help us do that is trig form. So my vector, for my aircraft, well, we know the magnitude, 600. And we actually know the direction. It's due south, so think about your unit circle. So that's 270 degrees. Plus, Louis saying hi, sine of 270 degrees. Now, if I do this using my unit circle, cosine of 270 degrees is 0. Sine of 270 degrees is -1. Distribute that 600 and we get -600J. And it told us it wanted in terms of I and j, so that's why I did that. Oops. Now, some of you, we could have seen that without doing that work. I mean, it's just headed straight down. So then my vertical movement is just negative 600. So you can see that and not have to show all that work. Now for the other one, let's go ahead and switch. B sub W. Now this one, pay attention. Our direction is always from our x-axis, always, 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 always. So I did this to get that 270 degrees. So many of us are going to want to put in 30 degrees. That's not true. That's not how we look at direction. This is just known as bearing. So we actually need to give this angle. So be very, very careful of that. So we're going to go ahead. They told us, and I could have put this on the diagram, our magnitude is 60. Cosine, so be careful, it's going to be cosine of 60 degrees plus sine of 60 degrees, J. Once again, because with trig form, our angle is given this way, always from the x-axis. Always, always, always. So now I can, luckily this is on my unit circle, so that's nice. They aren't always. Well, cosine of 60 degrees is 1/2. And sine of 60 degrees is √3/2j. Distribute that 60 and I get 30i plus 30√3j. I'm definitely going to leave it as a radical so I do not have any round off errors. That is one of the biggest problems with these. So don't round it all until the very, very end. All right, so what we just did is we figured out trig form of this vector and of this vector. Well, now what we're going to find is we want to find the velocity of the aircraft relative to the ground. What that means is we actually want to find how fast this is going with this jet stream acting on it. So how to figure that out is we're going to add these two vectors together to see how that jet stream is acting on the aircraft. So what we have is we're going to do V sub A plus V sub W. So it's negative 600J plus the other one. Now, you can leave it like that, okay, because it's more accurate. You can't combine anything because one's in terms of I, the J's, one's a radical and one isn't. So you can leave it just like that because that's the entire answer. I think a better way though is to write it in terms of I and J. So this is my I. And what I can do is put my coefficients for my J in parentheses. It's not necessary, but in case maybe you're looking up the answer, somebody give it that way. But again, don't round, can't combine, they have to be like terms. If I did have like terms and I could combine, I should, but 630√3 can't be combined, negative 600. So what we just found, oh, forgive me, I wrote a W there, is this is the actual vector, okay? This is known as our resultant vector. This is actually what is happening to the aircraft, okay? Because yes, it's flying, but it has this jet stream acting on it. So this vector will actually tell us the actual speed and direction of the aircraft. So what I need to do is, with this new vector we found, our resultant vector, we need to find the actual speed and direction. So what I'm going to do, well, to find the actual speed, that is, what do you know? Magnitude. So you could give yourself a visual if you'd like. Let's go ahead and do that. If you just wanted to get that visual, let's just go to our Desmos and see what that number gives me. So negative 600 plus 30 root 3. It's like negative 548-ish, just so I can get an idea of where this would end up. So once again, let's just give ourselves what we started with. We have this is where our aircraft's going. And then we have this jet stream acting like this. Well, if we do this resultant vector, it's 30I, so it's far out here, but it's still going down negative 500. So it's like, you know, totally approximating. And I think this would be much longer because it's going so far down. Oh, it wouldn't be past the 600 though. Something like that. So this is this vector. And so we're going to find that length and we're going to find that direction, which remember, let me give myself another color, would be this. So when I find the magnitude, you know, you could create a right triangle if you want, but once again, I hope this is getting better. It's 30 squared plus, and I'm going to put this whole thing, negative 600 plus 30 root 3 squared in parentheses. Again, don't round until the very, very end. And I am definitely going to rely on Desmos for this. So it's a square root, 30 squared plus, I'm going to put in parentheses, negative 600 plus 30 root 3, close that. Be careful of closing these things. They can get a little, yeah, and then square that. So we got 548.86. We'll go to the hundredths. So that's my magnitude. Don't forget units. This is miles per hour. And hopefully that sits well with you because that jet stream is slowing us down a lot. Now, if you want to find that direction, let's go with pink. Once again, it's going to be the inverse tan. Well, remember, if I create that right triangle here, we know this is 30 and this is negative 600 plus 30 root 3. Well, it's opposite over adjacent. I definitely don't know that, right? So I'm going to rely on my calculator. So inverse tangent of negative 600 plus 30 root 3. Get out of there with that arrow. Divide this whole thing. See, so pay attention to that. That's only dividing that. So I don't want to do that. I probably want to give myself double parentheses, then divide. So pay attention, and I believe it's over 30, right? Hopefully. Oh, and make sure you're in degrees, right? So this is negative 86.87. Now, this is the real fun part. The problem gave direction in terms of bearing. We need to do the same thing. So once again, if you need refresher on bearing, you're going to check out the right triangle trig videos from our first week. So bearing, what this is giving me, because of how inverse tangent is programmed in our calculator, it's only giving me this angle. But what I need is this angle. So think about it. If this is 90 degrees, right? And I have this piece, and I just want this little piece, what I'm going to do with this angle is I'm going to add 90 to it. And this isn't always the case. You have to pay attention to, so I'm going to go here and then answer plus 90. 3.13. So it might not always be adding 90. You got to pay attention to which quadrant you're in. Okay, so again, with bearing, it's always in terms of your north and south lines first. Well, since this bearing, I'm going to color it yellow if you can see that, is attached to my south, it's going to be south 3.13 degrees, and it's headed east. So the actual direction is 3.13 degrees east of south, and the actual speed is 548.86 miles per hour. And so then the aircraft can know how to adjust, all those fancy things in that cockpit to adjust so it's still heading due south. Yeah. So again, if you need a refresher on the bearing, check out that video, and I'll see you next time.